to Wanix. So I'm using Cursor now, which is basically VS Code, but has Copilot auto completions and, you know, an AI you can chat with. I don't even use Copilot, so I'm still getting used to that whole experience. So we'll see some of that. So yeah, today we're basically starting from scratch, rebuilding Wanix, which I think was a little over a year ago that I started working on. And then did a couple of demos. One of the latest demo is on the Wanix site here. And, you know, in general, yeah, it's a WebAssembly based Unix-like development environment entirely in the browser. It's kind of hard to explain. Like, it's not a easy concept. It's, you know, I'm really playing with a bunch of old ideas and new ideas and really just trying to come up with a new new way to build systems, new way to build software. But Wanix is kind of almost, I mean, it was almost a joke, but it's sort of turning into a pretty cool idea, or this iteration will, especially because we're leaning into some like Plan 9 ideas. So the repository is up on GitHub. What's in main is actually the current version. Let's see, did I not push? Basically, I put a note in the README that active development is now going on in the 03 branch. So that's where we're working here. So that's why it is pretty much empty. The only files that I kind of brought over are just some of these project files. So this is pretty much starting from scratch. Rohit, have you made a Go project? Have you done like a Hello World or anything like that outside of the online tutorials?
Yeah, I did try doing Hello World.
So this is, you know, a good example of kind of starting a Go project, mostly from scratch. I've already did a Go mod init to define this Go mod file, which is similar to like a package.json, I guess. It's the equivalent in the JavaScript world. Unity projects have a lot of files, right, Rohit? When you create a
it does have a lot of file, but it's just with the latest technology, the IDEs kind of do everything for you.
Yeah. But, you know, so not all, you know, that's common for game development and a lot of people getting into software development, working with IDEs, but there's a lot of different kinds of programming, and I remember web programming was one that really popularized the idea of like not using an IDE because you didn't really need it, you know, decades ago now, but it's just interesting that VS Code kind of evolved from like more of a text editor than an IDE. Like what I think of as an IDE is much more complicated than VS Code. Visual Studio, for example, is a full IDE. VS Code feels like...
I started using Visual Studio. So it's like Visual Studio is like you start an application, what software, what program you want, it just does everything for you.
Yeah. Which now, you know, you don't really know what's going on. Which, you know, I think when you get started, that's fine. But eventually, the more you do and want to do and stuff, you end up having to kind of learn how everything works. This is kind of my outline. I wanted to first get a kind of an empty shell of a command line, a Wanix CLI tool, just to get that in place and make sure that works. Then we're going to talk about file systems. because this is inspired by Plan 9, which does a lot of stuff with file systems. And then over the last few years, I've been working with file system as an abstraction. And we'll talk about that, some cool stuff in Go. And then we'll actually use it to make a file system that we can access on the computer, on your system. And then if there's time, we'll get into some other stuff. So kind of starting a project, starting a CLI tool, and then doing some file system stuff. So I deleted all the code from that was in main. We actually did have a command line tool in here. I'm actually going to use this just to start it. In Go, there's, a lot of languages have their conventions for like how you organize projects. This is pretty standard for like a Go command line tool. And instead of doing this yet, when building systems, especially getting started, I like to do kind of the simplest thing and then make sure that it works. So we could do go run. I think we could just do that. Cool. Obviously we can do a go build. Oops, go build in the Wanix package, and now there's a Wanix. Tara, are you remembering our conversation about relative paths for executables? This is one of those things that developers have to learn. Rohit, we were talking about not learning Unix-y stuff or Linux-y stuff, but especially as a developer, you eventually have to learn, when you run a command on the command line, how does it know what command that is? Where is it run? Because I just ran Wanix, right? We made a binary called Wanix, but this is not the right one. This is the right one. And so this gets into a whole thing about your path and stuff like that. I don't want to get into, but if you didn't know that, then it's pretty confusing. There are a lot of weird archaic things that you're like, why is it this way? And that's why I like computer history stuff, because it's it explains it. And then you're like, oh, it does make sense, at least from that context. And you can kind of at least appreciate some of the weirder stuff that you deal with. So anyway, we built a Go Hello World thing. The stuff that was in here before was actually part of a command line. Oops, a framework. Okay, here we go. Project called Toolkit, which is basically a collection of libraries that are used very often in a lot of these projects. And one of those is a system that basically manages the major components of your system. So normally you start writing main, your entry point, and you just write your code to do whatever. But here we're sort of setting up so that we're just kind of creating components that can wire up together, because usually you end up writing a complex system with multiple subsystems and components, and it's really good to kind of break those up in a way that makes sense. Anyway, this is basically a way to create a slightly more I'm going to make a subcommand called serve, which going to grab an example because I write a lot of code, so a lot of the time I'm copying and pasting from previous work just because it's quicker. So I'm mostly copying the code to set up a new function, a new subcommand here. So now here we'll say hello world, and we'll call this serve Wanix. What does that mean? We have no idea yet. Right, Rohit?
Yeah. Oh, wait, so you just created a...
This is, so, you use, kind of like web frameworks, you use a web framework to help you make a web app or a website. There are a lot of like micro frameworks or little libraries for things. And so this is a little framework for making CLI command line tools. And so it involves basically defining your command with a struct, right?
So if you on CLI just use serve, it will run with that command you already defined, yeah?
Yeah, so I'll show you that in just a minute. I'm sort of wrapping it up in a function here just to make it easier here. But anyway, so there's sort of like a root command object, which is Wanix, which represents our command. And we can put the version so it can automatically have a version flag and command. And then we can add subcommands. So we just added a serve command, which doesn't do much, just says hello world. But yeah, and we're also going to have to probably install tractor. Go get. This is the equivalent of like npm install. Let's see, maybe it needs this. Okay. And then we'll see if it compiles. It did, Wanix. So now you can see, because we're using a framework, we didn't have to write, any code to get this help text. And it shows available subcommands. So I can do serve, right? So
okay, yes.
We're just using a little framework for building CLI tools that makes it so we don't have to do as much work.
Oh yeah, I got it. Yes.
So that's pretty much. Go ahead.
It's kind of namespace style, right?
Yeah. Because there's a lot of ways you can do command line tools, but a lot of the bigger, more complex ones will have subcommands and maybe even subcommands. But yeah, basically lets you create, effectively, subcommands on this command. All right. The serve mount, we'll come back to that. So now we're going to talk about file system stuff. I wanted to make sure that we had some code working. Have you ever worked with the file systems APIs, Rohit?
No.
Yeah, nobody works with... ultimately, if you build any kind of system software, you have to work with the file system because it's in every platform, right? But we think of file systems as a way to store data. It's kind of an interface to your storage devices.
Yeah.
And most people, when they think of the file system, obviously they think of, like Finder, this kind of stuff.
That's what comes up in mind when you say file system. Like
which is very different. There's a bunch of people on YouTube and Twitter, whatever, social media that are like complaining about the hierarchical file system, like folders and folders, like it should be tags. Like it's kind of like it always been an age-old debate about that. But there are reasons why it's hierarchical. And so for developers, when you talk about the file system, and I say developers or like sysadmin people or Linux people, you know, this is the file system to them. It is what you work with on the shell. And there are a lot of things that just make more sense there, where it makes sense that things are hierarchical.
So isn't this basic? So the finder you showed, the file system you showed earlier, isn't that basically a UI for this system, the shell?
Yep. You know, we could do open here, and it opens this directory in the in Finder.
That's basically a UI. That's basically like a good-looking UI for the shell.
Yeah. Though you'll notice that it's really designed for working with, you know, well, what most people think of when they think of file systems are files of data. Like, oh, here's a file, I can like move it into this other folder, or maybe I can double click it to open it. You know, maybe I can right click to do some other stuff. But, you know, for the most part, you can do things like, oh, maybe I can like quickly make a zip file or whatever, but it's mostly working with files of data. There is, let's see, do we have this on Darwin? Proc? No. In Linux, there's a root directory called proc, which has the state of running processes. And it's not really files that you can edit. It's exposing the state of things. And that's what was interesting about Plan 9. You could see, you know, each TCP connection was represented as a file and the way you'd work with it. So you could do a lot of interesting, powerful programming from the shell, and you wouldn't necessarily have to write a program in a programming language. But it also meant you could do things interactively. Yeah, so file systems, usually most people are going to think of this, but where the way we should frame it is think about it on the command line, because that is where a lot of the power comes from. And so we're going to make kind of virtual file systems in a bit. In fact, that's kind of the core idea of the whole new iteration of Wanix. Why am I starting over? Because there's now a simpler way to implement what we're trying to do with Wanix that is much closer to what Plan 9 did. And it has to do with the file system. So we'll get into that. But some kind of intro stuff, I made some notes here to help kind of conceptually get through some of this stuff. Are you familiar with the interfaces in object-oriented programming?
Yeah.
Basically, it's like the shape of some type, right? You can create a type of a struct and put methods on it, but then you can create a type that represents, you know, the shape of, you know, what methods are on there. And Go is one of the few languages that does interfaces really well. And there are a lot of these kind of single method interfaces. So these are from the standard library, the IO package. And these are probably the most significant interfaces in there. Read and write. Which, you know, these kind of have weird signatures, because you would think the point of these is to read a stream of bytes and write a stream of bytes. Because ultimately, in computing, everything is eventually a stream of bytes that was, you know, stored in memory, but usually copied somewhere else. Whether you're serving a file over the internet, you know, that's going to load in the browser, all of that's just copying bytes. So read and write streaming of streams of bytes is kind of a big thing. Every language will have some way to do that. But what's interesting is interfaces let us talk about just the reading or just the writing or just closing a resource. Because what can you read and write? You can read and write from files. You can read and write from a socket, like a TCP connection. You could also read and write from a buffer of bytes if you wanted. So by creating interfaces for these, you've created a standard way to read any slice of bytes, regardless of what it is, if it's a file or a socket or in-memory buffer or whatever. And then you get some cool stuff out of that. But Go also lets you do composite interfaces. So you're kind of like, a read writer is a combination of a reader, so something with read and something with write. And a read write closer is something that has all three. This composition is really powerful. So one of the benefits of interfaces is being able to make utilities that only need that interface. Like this copy, and you can imagine what it does. It copies bytes from a reader to a writer. It doesn't matter what that reader is. A reader is just something with read. And so this copy to go from a reader to a writer could be used to copy from a file to a network socket, or from a network socket into an in-memory buffer. I know those are the three main examples I keep using, but there are a lot of other things that it could be, because everything is just copying bytes. And so now we have this general purpose copy that works with all kinds of types of things. And that's because of interfaces. So some other ones, like if we want to read usually if you were reading a file or something like that, you allocate some bytes and then you pass it into read. I know normally when you think of like, oh, I want to get some data, you'd have it as like a return value. But there are a lot of specific reasons why this API is designed the way it is. So it's a little weird. You allocate bytes, pass the bytes in, and then when this returns, bytes will have potentially be written, or n bytes will have be written to it. If you wanted to read a file, you're usually going to do that multiple times because you don't know how big the file is, or you're going to read it in chunks. So normally to read a whole thing, you would do a read in a loop, and that's what read all does, basically. Reads until it gets an EOF. Multi-writer, here's kind of a cool utility that it's like, oh, I can't think of a specific use. These are like plumbing utilities. So multi-writer, let's say we have a writer, like we have a socket that, a TCP socket, and we can write bytes to it. But then say we also have a file, which we could also write to. If we put the file and the socket into a multi-writer, it'll give us a new writer, where when we call write, it'll write to both of them. Really simple concept, but that's kind of useful for doing things like what this last help utility does, which is given a reader, so maybe we're reading a file, as we read it, whatever we read is going to be written over here. So it's sort of, like maybe we're reading a file to serve over HTTP because we're making a file server or a web server, but then we want to see all the bytes that were read. So we could maybe do standard out as the writer here, and it would log out every, as every byte is read, we would see it over here. So it kind of lets us, they call it teeing, but kind of like copy, fork the stream of bytes. So that's kind of the cool stuff of interfaces. And of course, working with files, this is kind of a core thing. So here's the implementation of file. There's an OS file, and this is pretty much the same in most languages, and that's kind of part of the benefit of this is that the file system is a universal API. It exists in every runtime. It's in standard lib. It's been around forever. Every language has it, supports it. Most of the time we don't use it because we're going to find more uses for it here. So OS file, it's a struct, and then it implements read, write, close, but also a bunch of other stuff. And that's how interfaces work. Anything that implements read is a reader, so a file is a reader, even though it does all this other stuff. But this isn't all of the things that you can do with a file, but just to give a sense of like, what are the data, when you think about files and file systems, like what does the API look like? What does the shape of it look like? So now like, okay, we know we can read and write from a file. We can close a file because we treat a file as like a resource that the operating system is tracking. So there's a lot of things that need to be cleaned up. And so close is sort of the canonical cleanup because that's the original, the file is one of the earliest computing resources. So you open a file and then you close a file. But close is also, and you saw it as a standalone interface, so that's often used in other things when we want to finish or clean up or whatever. So these interfaces also sort of define our idioms, what are the patterns that we use. And if we use those patterns, we get a lot of benefits like being able to use utilities. There's, files also have metadata. So like, how big is it? Actually, this is more or less what it is. So it's, the name of the file, how big is it? The file mode, which a lot of, programmers these days kind of hate because it's a flag, a bit mask flag. Most of the time your programming language will have constants for it, but basically mode is one value that's going to tell us a lot of stuff like permissions. Is it readable by the user? Is it writable by, all the, in Linux, when you do, all of this stuff, all of this data is basically the metadata. So that's all in file info. And this is a standard interface, so any file's file info looks like this. We have the modification time, the last time it's modified, is it a directory? Because ultimately, it's important to remember that the file system is just a bunch of nodes, files, or directories. And so once we get into this like low-level stuff, we'll be talking about a file, but a file could be a directory because ultimately they're the same thing. And then Go has this kind of open-ended field for file info that you can get underlying metadata, because different operating systems have different file systems, and so they might have different types of metadata. And so Go's standard interface is designed to be sort of like the common denominator. It'll work across all platforms. But then if there's platform-specific stuff, you'll see like an escape hatch like this that lets you get at that data. So a file is bytes that you can read and write, and you open files and you close them, and then you can get that file info. With stat, so the names of these are very like, stat, I don't know, status maybe. You probably, why isn't this just info? But just in the way things evolved, this name stat has momentum, so usually you'll see that. And then there's chmod and chown and all these things that also have command line equivalents for changing the file mode and who owns the file. That's basically changing this file info. So obviously a file is going to let you do some of that. If it's a directory, because a file could be a directory, a way to actually get the entries, what files and other directories are in this directory. And there's a bunch of other stuff that we won't get into. But anyway, that's, a file. And then how do we get those? How do we open a file? Every programming language has a bunch of functions that look like these to work with file systems. So ultimately, you can open a file, and then that gives us a file. There's these helpers here, kind of alternative ways to open, mostly because the flags in the file mode is annoying. Like, nobody likes setting those. So most people will use open, and then create is different because it's going to say that it opens it with flags that's saying, we're not going to append to this file. We're going to either create it if it doesn't exist, or write over the file that exist. So those are kind of like the main entry points to working with files. And then we talked about the metadata. So there's usually functions to work with the metadata here. You can kind of see, though, if you open a file, you can get metadata that way and change some of it that way. But it's often pretty common, since you can do it from anywhere, like on the shell, to change all of these without having to do an open. And then there's stuff related to basically names, because really a file system is just like, even though we think of it as a tree and these paths as hierarchical things, really they're just like key values. The key is the full path name, and it's a string, and then what you're getting out of that is a reference to a file. So if you think of a namespace as a file system, is basically like a big dictionary or a big map. This makes a little more sense why they use name a lot of the time instead of path. But obviously, here are the common things that you would do with a file system. You can make a directory. So make a new empty directory. Make dir all, which is kind of interesting, because if you try and make a directory in a directory that doesn't exist, it will fail. But make dir all will create all the directories that are needed to make that directory. Does that make sense? Have you done like make dir on the command line? Like, obviously you've probably made directories, but make dir. And then, there's like, for all of these things, there's a command line equivalent.
It's basically all the basic command lines, like arguments which we use. I think I worked out with all of these.
Okay, so you have worked with the file system API.
Yeah, I have worked. Yeah.
So this is kind of nice, because this is really an overview. There's more stuff, but these are kind of like the main things that you would do with a file system. Obviously, remove files, just like deleting a file. Sometimes this is called unlink, because technically you're not deleting the file bytes. You're just unlinking that file from this file system's namespace. In Linux, we have something called symlinks and hard links, so you can kind of create like not quite a copy, but because files are stored separately, like come from somewhere else, you can have a symlink that points to something. So have you ever made a symlink before? Like, it's kind of a one is, I guess if you're on Windows, you don't really do this as much, but on Linux, Unixy systems, if you want to kind of make a directory that points to another directory, is basically what it is.
No, I haven't done that.
Yeah, and it's kind of a Linux specific thing. And then we're going to talk about something called binding, which is an even more advanced version of linking. So when we're talking about Plan 9 and the things that were cool about it that it does, it has a much more powerful way to do this kind of linking. And then obviously renaming, which aka move. So you'll find these in most languages' standard libraries, usually under like the OS package or module or whatever, because every runtime lets you work with the file system. Then there's usually some high-level convenience things, because if you want to read a file, You have to open the file, figure out the file mode. And then once you have the file, you have to read, but you have to read multiple times. So you do that in a loop until you get to the end of the file. And then you got to make sure you close the file. So obviously, most of the time, when you want to read a file, you're just like, here's the name of the file, give me the bytes. So it's really common to see a high-level operation like read file, as well as write file. And then there's read dir, because dirs are sort of different in that when you read them, you're not getting bytes, you're just getting a list of other files. In theory, you could, create a file system API that does most of what you want with just these, and you don't need to use all of these, but most of these are implemented by using these. They're sort of derived. And then there's a bunch of other stuff, but, and then the file info. So can you think of a problem with this setup?
Problem with the file system?
Working with the file system in this way. You've got all these functions to work with the file system. But if you if you ever wanted to write test-driven code, you couldn't create a test to see if when I wrote to the file system, unless you actually wrote to the file system, which maybe you don't want to do, or maybe that's expensive. And so, in terms of performance, so it's slower. So you're like, the code that I write against the file that uses a file system, how do you test that? Most of the time, people will just write tests that will write to the file system because who cares, and then you delete it. But you just have to make sure that you're cleaning up and all of that. But usually when you're writing tests, you're trying to do them in a stateless in-memory way. So there's really no way to work with a virtual file system. And so eventually somebody in the Go community made the Affero package, and there's a bunch of packages like this. They're all kind of doing the same thing. But all they did was create an interface for those file system operations. You can see they're pretty much one-to-one mapping. Right, this isn't all of them, but you can see these are the signatures. They're pretty much the same names and everything, but they're in an interface. Now that you have an interface, if you program against this interface, then the implementation of the file system can be different. We could do an in-memory file system, for example, that you would use for tests. So it never actually hits the file system, the actual system's file system.
Oh, yes.
So we've created this indirection. And it's just kind of interesting that this isn't built in. Like, for a language that's all about interfaces and the benefits of interfaces, made by the way, Go is made by the people that made Plan 9, and they treated the file system as an abstraction. Why didn't Go have an interface for this? Part of it is most languages don't. Most languages, they all, because of standard lib, which most languages sort of build on top of the standard C library, they're just re-exposing what standard lib does, which ends up looking like this. And not all languages have interfaces and all this, but I thought it was weird that Go didn't have this. But it is kind of big. Like, this isn't even all of it. And one of the sort of design philosophies in Go with interfaces is trying to make interfaces as small as possible, because then you can focus on the semantics of that specific thing. And then also here's file. So here's another thing that's slightly different, is these all have the same signatures, but when they return a file, they're returning a file interface. And this is how Affero defines their file interface. Here's that composition so you can create interfaces based on other ones. And so there's a bunch of standard I/O ones. We saw reader, closer. So this is basically saying file has read, file has write, file has close, and some other stuff, and a bunch more methods that, you know, a file should have. So it's kind of like, looks a lot like the file system API, but it has this, it is an interface, an actual interface. Affero also comes with a ton of utilities. Read file, write file, walk. But these are kind of needed because now any operation needs to take a file system. You know, if you were to do makedir with the OS, you'd say OS makedir, and you just give it a name and whatever. But if you were to do makedir with this, let's see, is there an example? I'll get to that. Anyway, you get the idea. Now we have an abstraction for file systems, which not only means we can write code that is that works, that uses these interfaces, but we can also create different implementations of file systems. So one implementation would be just wrapping the OS FS. So in Affero, one of the built-in file systems is one that just wraps all of the OS package functions. Then the other common use case was in memory. So here's a file system that is basically empty, and you can write files to it and read files to it, and just storing it in memory. But then it gets interesting because interfaces let us do a lot of cool stuff. We could create a file system that takes another file system as its sort of base file system, and then overrides some of the methods that it has and changes the behavior. So for example, read-only FS will take a file system, but any of the methods that have to do with writing data, like making a directory or changing metadata, it'll return an error, ensuring that you have a file system that you can only read from. So that's kind of a cool utility. You can kind of like make sure that whatever this file system is, you can't make changes to it. Another wrapper that comes with Affero is base path. So this idea that like really a file system is almost like a directory, because you could create a file system. You can think of a file system at any directory level. You know, if you have a foo directory at the root and you want to open a bar file, you would open foo/bar. But if you had a file system that was the directory of foo, you would just say bar. So there's this idea that the file system is more or less correlated with a directory. And so normally when you work with like OS file system, the root directory is your system root. It is /. It's the thing you never want to RMRF. But then if you put a base path, this is a wrapper that will basically prefix any name with a base path. So it's basically constraining all the operations to a particular directory or particular path. So that's kind of another useful one. That's almost what namespaces are, or truths, which is how containers work. So there, a lot of these technologies are how Docker is designed. We use, so for example, here's some more interesting file systems that, you know, aren't file systems in the sense of like they're places to store data, but they're providing different behaviors. Here's one where whenever it takes a file system, a base file system, and then we have another file system that we give it, that whenever we read a file, it's going to write to that file to this other file system. So it's almost like T back here, where when we read from a stream of bytes, it's going to write it to another writer. That's kind of what cache on read is doing. And then there's copy on write, which is one of my favorites, which basically takes two file systems, layers them on top of each other, which means if you have two directories with the same name, their files will sort of show up as ones, they'll all show up in the same directory. This idea of layered file systems is how Docker images work. But basically what this is you give it a file system and you can read anything from it, but as soon as you write to it, like you create a new file or you change a file, that write goes to a different file system and all future reads will come from that one. So basically you're saying, it's kind of how in containers, the image is sort of like the base file system. And then as soon as you make changes, it stores those changes in a separate layer. And that's how layers work in Docker. But this is cool because you can do unions. Anyway. And there's a bunch of stuff in Affero, like there's a tar.fs package. So tar files and zip files, both, archives. There's standard library stuff to work with zip files. Golang, zip, archive zip. And it's specific to this particular file format. What is the example? If we want to read the zip file, open reader. And you can see, it's a reader, so it's something we can call read and close on. But yeah, it has this like file thing that we can range over. It's not really a file system, even though it does say open. But we couldn't take some code that expects to work against a file system and read stuff out of the zip. But if we used zipfs, then we could set up basically give it a zip file, and then we could pretend in code that it is a file system. And so any code that works with file systems, so all of these utilities, we could actually do to files in the zip file. Does that make sense? Like we could read a file. Right. We could read a file out of the zip file. We could, we could create a direct. We could check if a file exists in the zip file, and those aren't zip file specific things. These are just general file system specific things, and that's kind of what we're getting at with interfaces and using common interfaces, because now you get all these capabilities for free. Other things that are kind of cool file system implementations, they have one that stores, Google Cloud's object store. Have you worked with like S3 or Google Cloud Storage?
Yeah, I worked with S3.
So S3 is basically buckets, which are kind of like directories. And you probably used an S3 client library, right?
Yeah.
Well, what if instead of using that client library, you could just configure a file system and then work with it like a file system? It's like one less API you have to learn, because you already know how to work with a file system. And so now we can work with S3 with this API. But not only that, all of these helpers and any code that was ever made to work with file systems will work with now managing S3. Are you kind of seeing this whole, like, it's a way of designing systems so that you get more out of them?
It's kind of, you get more out of, and it's kind of one solution for everything.
One abstraction, yeah. And I'm not saying that the file system is the abstraction, and a lot of people assume that Plan 9's hypothesis is that the file system is the ultimate abstraction. It's just one abstraction. But it has all these benefits that are really interesting, like every programming environment can work with them. Every programming environment might have utilities that work with file systems. And so you're kind of, with programming, the world's complicated enough. Software is rampantly complex. So we need to try and design systems, and this is what the Plan 9 people were trying to do, is design systems that are simpler, and as an added benefit, you can do more with them. It's like the best of both worlds. Why don't we do that? And so that's what I do, because I can, I guess, afford to do that, and try and make systems that show that, and then convince people this is how we should be writing software. There's also some interesting, like, experimental things, like Golang JSON file system. I thought I remember seeing somebody implemented a file system for JSON file. So basically being able to see every, let's say the JSON file is of a JSON object, that has a bunch of keys. And so each of those keys would show up as a directory. And so they made it as a way, here's a way to work with JSON files. And again, it's not necessarily the best way, but once you have that abstraction and it exposed in that way, like all the tools that you have on the shell to do stuff, you could interactively kind of navigate JSON in the shell if you wanted to with that file system. So that's one of those, like, is that better than how we do things? Maybe not, but maybe there's a use case where it makes a lot of sense. But it also is just fun and neat, and by exploring those neat ideas, that's where you find the really cool use cases. So this abstraction was made as a third-party package. It's not built into Go. It's not in the standard library. As a result, not all Go code is gonna work with this, but if I make my application around this, at least all my code will work with this abstraction. But finally, Go said, we're gonna add a file system interface to Go standard library. This was just a few years ago, and I was really excited because that would mean that if it's in the standard library, it becomes the standard for the whole language. And so we would start seeing utilities that would work interoperably with different code bases because we'll all kind of use the same interface. So I was really excited. Here's what it looked like. Here's their version of file system and their version of file. Their equivalents are here and here. Affero, by the way, did a lowercase s, which is not proper Go naming convention, but anyway, notice anything about this?
I mean, it's kind of similar what Affero was trying to do.
But there are a lot fewer methods, right?
Oh yeah, a lot fewer methods, yeah.
Which, for a lot of people, were like, go ahead.
We can add more methods depending on what we need, right? It doesn't have to be.
True. And that's exactly kind of the way they're thinking, because as it turns out, this is a hard problem. Like, the file system is a complicated API. It's a lot of methods. It's slightly different on different platforms. And yeah, so I was surprised that it was sort of, in their wisdom, they're basically saying this is the minimum representation of a file system. no matter what file system you have, you at least have the ability to open a file by giving it, a file path, and then you get a file. And that file you can call stat, so we still have file metadata stuff. You can read. It's interesting, there's no write. So in this sort of minimal version, it's a read-only file system.
Yeah, but there is no create as well.
There's no what?
There is no create for file system. So how are you gonna make
well, there's a couple of things. Well, one is open. Usually, even if there's a create, that's usually calling open file, but with a flag that says if it doesn't exist, create it. So it really creates kind of a convenience, but that's kind of a implementation detail. But you're right. So it's missing create. We have no way to create files. But they kind of showed how you can build on this. They did something called interface extensions, which I hadn't seen in the standard library yet. But you can see we have another interface in IOFS. And with the composition, we're saying that statfs is a file system. So we're saying it has open and it has stat. So it's kind of like in the beginning where we broke up read and write and close. But it's interesting that, there's a kind of an extra constraint that something that you call stat on also needs to have open, or whatever the base sort of abstraction of a file system. So now anything that has the statfs interface, you can call open and stat, which, by the way, this is kind of a convenience, because a file system, you can already just open a file and call stat. But it's such a common convenience that you could just call stat without calling open, that they did this extension. But they're kind of showing that here you can extend what a file system is, the interface. The problem with this is syntactically in Go, this is what it would look like to use it. So OS_durFS gives us a file system, so something that looks like this, for the operating system's file system. So it's kind of the new version, or the built-in version of Pharaoh's OSFS. It's just wrapping all of the original OS functions. But anyway, so now we get a file system as a value, and it's of the root, /root. And because it's an FS, we can only call open on it. So how do we call stat? We have to do this type assertion stuff in Go. So if we get something of a certain type or interface, you can do type assertions if you know that it's also has this other interface. So here we say fsys statfs, and then if it has stat, we'll get a new value that we can call stat on. It looks like I did this wrong. This code should be statfs, because that's the only way. And then it returns true or false if it had that. But this is kind of annoying to write, especially if you'd have to do it for like every method that you call on the file system. So they created a utility function called stat, and it takes a file system and the same arguments. So it's basically a function version of this method. And now we're almost back to the OS version where we can just call functions. But you can see here, we can say, we get the file system, and now instead of calling stat on that file system, we call the function stat, fs is the package, passing at the file system. And so now we don't have to do, basically it's doing the type assertion. But another cool thing that this can do is because stat is derived, if we write code like this, if a file system doesn't have stat, then I guess we can't call stat. Except that's not true, because we can also open a file and then call stat. So having this utility function also gives us the opportunity to say, if it doesn't have the stat interface, I know another way to call stat. I'll just call open and then call stat. And so that allows us to get a stat that will work regardless of whether there's a stat method on it. Does that make sense?
Yeah.
This is just dealing with like the type system in Go. And so this is a very kind of Go specific pattern.
Do you guys want to take a break now? It's been about an hour.
Yeah, we could take a quick break because I'm about to talk about the code that we're going to write next. So yeah, how do we want to do a break? Just a 5-minute break. Maybe I can get some water or something.
Sounds good.
And then we'll actually get to writing code because we're at the end of this. But how's this? Okay. So the last bit of this file system stuff is I decided to take these patterns that they set up with these interface extensions and implement the rest of this interface. And part of this was because Affero was made before IOFS. And so it was actually returning types that are different. And so if you wanted to use IOFS, you couldn't really use Affero unless you used this adapter, and then you're already kind of converting between types or whatever. So I did something I've never really done before, which is kind of like an alternative FS package where I make type aliases for all of the symbols so that it's basically a copy of the package, and then I can change or add stuff. And then more or less the code is the same, but the import is different. We'll see that in a bit. But so the code that we have now, so I've created basically my own FS package that is a little bit like Affero, but made for and works with IOFS, and has some other kind of specific utilities and abstractions and stuff that we've been using for a while. But I've kind of run into some of the limitations of that. And so for Wanix, we need to kind of fix those. And so, we're rewriting Wanix. We're also going to rewrite this FS package, which is mostly going to be kind of like copying stuff over and getting it all right. And then later I'll copy it back into the library where this is. But basically we're kind of forking the FS package that I made and making it better. So the one that I made looks like this, where there's the main interface, which I don't know, there's probably other ways to think about this. You could call it POSIX FS. Other names that I don't like are like full FS. But one of the things that it seemed like made sense was this file system is mutable. The file system that you normally get is read-only. So a mutable file system is one you can change. So a lot of the methods that we needed to add had to do with changing the file system. So mutable FS. The big problem with this, though, is just like Affero, if I want to implement a file system, like I want to make a new file store or cloud storage backend or a wrapper or some kind of utility file system, that means I have to implement all of these methods to satisfy the interface. And I don't know, that's kind of annoying. Like, what if I'm making a file system like the read-only file system? Like, well, these, obviously, none of these need to be here. Like, or for example, remove, we talked about make dir and make dir all. There's also remove and remove all. And the reason for this is similar, is when you try and remove a name, a file path, if it's a directory and it has, files inside of it, it won't let you remove it because it's saying, hey, it's not empty. You wanted to remove this name, but it actually, there's all these other things. So remove all basically is remove that directory and all its contents, basically a recursive remove. But both of these are kind of derived operations, right? It's basically just saying, hey, if the parent directory for this doesn't exist, call make dir on that. And if that parent directory doesn't exist, call make dir for that. And so it's kind of annoying to have to, for every file system, create a make dir all that's just wrapping make dir, and similar for remove all. So there are kind of these lessons that in terms of designing these APIs where we could make this interface simpler or design this in a way so that our file systems are sort of progressive in that we can sort of like, the minimal concept of a file system is one that's just open. If we need a file system that has stat, then we make sure it's a statfs, and that continues for all of these. Oh, if we need to call makedir, then we have a makedir fs. And so I'll kind of show as an example what this looks like is a little bit more noisy and kind of, you know, I had originally tried this and just felt like it was there's too much boilerplate. But I think now I'm feeling like it's worth it. So now instead of creating this one interface for all of these, we have to break it down into an interface for pretty much each method. And then for each method, not only is there an interface for it, but there's a utility, because like stat, you would call this utility. But then that lets us do things like makedir all. We can call makedir all on a file system that doesn't implement makedir all, because we can implement this in a way where we can say, oh, it does have makedir though, so I'll just makedir all using makedir. Does that make sense? So that allows us to get this operation makedir all, but we don't have to implement makedir all for every file system. So it's sort of a progressive API, but also means that we have like fallbacks for derived functionality. And so, you know, we would do everything like this. We get a file system, and then pretty much every operation we would say fs dot whatever, pass the file system, and then the arguments. So it's a little weird, especially for people that are used to object-oriented programming, and they're like, I want to call methods. But this is just how it is. If you really wanted to call methods, you could create a wrapper type here's a struct type that takes a file system and implements all of these as methods, but then they just hand off to the utility function. But that's even more boilerplate cruft. And is it even really worth it? Because all it's getting you is the ability to say, you know, call makedir on your value as opposed to fs and then passing the value. So there are other reasons why this is probably a bad idea to do a wrapper like this, but and then we'll talk about this on a different stream, but there's a file watcher API that this doesn't really cover that we added in Toolkit, and that also needs to be redesigned. So what we're gonna do is this fs abstraction package I've made is in this toolkit repository under engine. And you can see here, I made a bunch of cool, interesting file systems. Most of these are experimental, but you can see there's equivalents to stuff we saw before. Obviously one that just wraps all the OS calls. And so there's some other interesting ones, but a lot of these we're gonna leave out. Here's the aliasing that I talked about. So the idea is, instead of, you could pretend you're using the IOFS package, which has a lot of stuff in it, all of these symbols, but instead we can import my package. And because we're doing type aliases and stuff like that, we can use all the same names, and they'll actually literally be the IOFS types. So basically it's sort of like for example, type aliases are made because these are equivalent to the compiler. So it's usually type aliases are for migrating something. So you want to move a type to a new package, but you still want to have that type in the old package so that you have backwards compatibility. And old code will still work. So you could create a type alias that points to the new wherever you put it. And so here I'm using type aliases as a way to sort of like create a clone of the file system package, and then we can add stuff to it and change stuff. So one thing that we're going to do is just do all of this again. And the way I work oftentimes is because I rewrite stuff a lot, and I have stuff in other libraries and other things are using those libraries. In this case, because we're sort of rewriting this file system package, we're going to rewrite it in the Wanix project because Wanix is the only thing that's using it. And then once it's done, we can deal with putting it back into this library and cut it as a new version. So here's the start of our new FS directory. But one thing that we should probably do is make sure there aren't any symbols that have been added. Like in a newer version of Go that we want to make sure is in here. But we can do that as a to-do. In fact, that's something, Rohit, you can probably even do. The IFS package for missing symbols. All right. And then here is where this interface is defined. And so instead of doing this, we're going to do a bunch of stuff like this. Which I guess we do all the interfaces and then what would we call this? File names don't really matter for source files. They're all contributing to the same package, but it's a nice way to group things. Maybe API because it's interfaces. We'll take these or do these somewhere else. But yeah, and then these symbols are FS, so they're all relative to this package. And we've created all those aliases so they all work. So let's do something like this. Kind of make haven't used any AI functionality yet. Yep. Okay. I'll just do this.
I mean, if AI can do this, then that would be amazing.
Well, you know what? Let's try. Let's say. Let's see. I think we want the composer. Make interface types for the rest of the. Let's see. It's not valid Go, so I'm wondering if it's gonna. How about we put these in comments, and then we can say for the method signatures in the comments. Yep. There we go.
Did do it.
So yeah, pretty good. Always got to check it. If we're going to be using AI, we got to check it. Yeah. That's one of those things where like there are a lot of modifying code where it's just like moving text around. It's like not even programming. And it's kind of cool that AI can help with that too. Okay. So we have all of these interfaces. For each one, we're also going to need the like helper utility function. Where would I want to put those? Maybe at the bottom of this file. Let's see if we can, I'll do one example. So rename, but it takes a file system.
The name. I think the name.
Oh, yeah.
Yeah, in the method.
Thank you.
Is
that it? Yeah.
And the old name, is that old name? Okay.
They'll both be a string.
Yeah, it's cool.
Create a utility function. Like the signature in the comment for each interface. It looks like it's gonna do it, and even make some comments, and even does the supported. Like it's literally doing what these would do. Is first thing it would try and do a type assertion to see if the FS value has that interface, and if it does, then we call it. Otherwise, it will return error not supported. Oh, this is in chat though. I should have done it in Composer so that it would do it. But I guess
I think there's an apply button on top.
Yeah, let's see if that works. What's the difference? Oh, it made a new file. That's not what I wanted. Well, we can just take these. It's kind of weird. All right. Why is error not supported? That might be a symbol that we're missing here.
Do you have to...
Error not supported. Error not supported. Oh, no, it looks like this isn't even a real thing. So it kind of is hallucinating. It says that we need to make that. I guess we can do that.
We can just do error not exist. Instead, we can just use... No.
Okay, well, yeah, you might think that, but it's pretty helpful because error exists is... Well, yeah, error not exist and exist are for whether it means something so specific. For example, most of the exists, if there's a utility for exists, it will call open, and if it gets not exist, then it uses that to determine. So we don't want it to say that that the path doesn't exist. We want to say that this method is not supported. So it makes sense to make a separate error. It would be nice if there was something in the standard library that is the equivalent of not supported. In fact, is there an error not supported in the standard library already? Error invalid, maybe. I don't know what the semantics. it doesn't look like they have docs on the semantics of invalid. I guess, yeah, this is often what they would use is what's
supported.
Yeah, what's annoying is once we put this on make this file system kind of real through Fuse, and we try and do something like open the file or do something on the shell, if it runs into, if we were to use invalid, then invalid actually specifically is about invalid argument. That's the text it'll show. And so that's going to be confusing. Previously, I used permission because I'm like, that exists. But then whenever there was a file system that didn't have a method, it would say permission denied, and I'd be confused. So these are very specific meanings. And so I think I'm going to try creating a new type, unless it looks like they don't believe that there is a not supported error. I kind of don't. I feel like maybe OS would have something like this. Variables. Okay. Oh, these are a lot of the same. Error done processing. Sometimes you can find, and again, it's all about like, well, if we all use what's in the standard library, then all our code is more interoperable. And so I get excited when they add new generic errors to the standard library because it means, you know, we can all use that. But I guess there isn't anything for not supported. So we'll do that for now, like it kind of said. So these all do not supported. What else do we need to do? So now we have all of these helpers. Let's see. Is there anything else? There's a bunch of stuff that will kind of bring. Okay, so that was kind of the equivalent of mutable fs, defining the interface. Then there's utilities, some other utilities. So livedir real quick, we'll bring this in later, but this is a utility that I made that because you can embed assets into your binary where it will, when it compiles the binary, it'll actually pull in any of the files that you reference into a variable which implements fs. And that's usually so you can kind of like, you know, package some static files with your binary and be able to serve them without the user also having to have those static files separate from the binary. We'll see examples of that later, but anyway, this is kind of a clever hack so that if those files actually exist on the file system, then we get a watchable version of them. So if they change, like you're making a development environment and you want to know when the files change, you'll get a notification. But this depends on the watchfs stuff, which we'll do later. So that pretty much just leaves util. And so it looks like this covers some of the ones that we have, but there's other utility things that are good to have. So copy these. I almost, yeah. So we'll kind of distinguish these as utilities being they're not utilities for accessing the interfaces. They're utilities that are deriving something like, does this not work? I guess this is just a static check. Yeah, it's not that big a deal. Let's see, some of these we can simplify because there's a interfaces are kind of neat in that you can kind of define them anywhere. So normally when you do a type assertion, you'd give it a type name, but you could also just define the interface in line. And because interfaces are compared structurally, it doesn't matter that this is like a different interface. As long as this signature is the same, it'll match. But now that we have those interfaces defined, we can just say open file fs. Yeah. And then I've also, see, I wrote in here remove, but I guess remove and make dir we actually got from wrapping those methods. The one utility that I wanted to bring in, let's see, was there anything in here? I took those out. Let's see, where was it? Wanix. There's a copy implementation that I wanted to bring over. But I'm blanking. Oh, maybe it's env86. Yep, copy. So it turns out copying a file is pretty involved. But a copy is also a derived, it's a utility that there isn't like a copy method in the file system. So you have to implement your own copy. I'll just copy this whole file. But we need to fix this. Let's see if our AI nonsense will be helpful. Copy? Where's copy?
You have to refresh the AI.
I wonder if I even need to specify that. I could just say copy. What? No.
No.
Did it do? What did it do? Anything? All it did was that. Okay, well, I didn't even do that. And it added it back because we have all these, it's auto importing them. So I'll just remove these. This is where normally it would be, this is one of those text operations. Although some, the editors now have stuff like rename symbol, which is really nice. Common IDE functionality, but because this is relatively, no, that won't work. I guess if we do fs dot with replace with nothing. Okay. And so otherwise it's just doing this mutable fs thing, which we can't do anymore, or we don't need to do. Where was this used? It's used by copy dir. can, I think, just be an fs. Let's see, why is it? Okay, make dir all. So here we would change this to, this function is in this space. Is that right? Yep. And chmod is another one. Yeah. So just one of the changes here. Oh, what's this? Let's I like this kind of programming because it's like programming that doesn't really require thinking. Just cleaning stuff up. Okay. Looks like there's a lot of comments that maybe at some point this supported symlinks and I decided not to. But I commented it out instead of deleting it in case I wanted to bring that back. So I guess I'll leave it. This needs to be. Okay. And you'll notice there's two actually, because copy all. Normally it's source and destination, but this assumes it's on the same file system. So if you want to copy across file systems, you'd have to have source file system path, destination path. So made two of, yeah, okay, so that's copy. There's one other helper that I didn't add that's at the bottom of this file because it had some other code, but tempter, I wanted to give it its own file since it's a got more going on. Maybe I'll leave these at the top. And this all looks fine. Oh, here's a, we could do a make dir fs. Okay, so this is, man, this fs library is coming together. I mean, we didn't write most of it, it's already written, but it already feels so great because it feels more organized. And of course, we've got our new broken down interfaces. What else would we need? Oh, testing stuff. I have not written a lot of testing code. I made a couple of testing utilities. There's also this is a relatively new package now in the standard library. One of the nice things is this mapfs, because Affero implements an in-memory file system, which is basically what mapfs is. But mapfs is implemented much more elegantly, which makes sense. The standard library is usually where some of the best Go code is. Where like it's a mapfs, which means it implements the file system API, like there's open. They added these convenience methods as well for whatever reason, but it's interesting that it's not even a struct, like it's literally a type derived by a map. That's how simple this system is. Like all its state is in this map. which I kind of want to. I guess for now we'll use this. I was thinking maybe we want to have a wrapped version of this in a package in our file system, in case we need to extend it or anything. But I guess we'll do that when we need to.
I think it will just be like more like boiler on top of the same thing.
Yeah, and so if we don't need to, we should not create more boilerplate. There is this test fs. Let's see, what does it do? Opening and checking that each file behaves correctly. I wonder what behaves correctly means. But this is interesting in that like it's a variadic function, so you could give it a bunch of paths and it will check if all of them exist. So basically it's checking, do these file paths exist? Well, it says if they behave correctly, so I'm curious what it's actually doing. Testfs. Oh, this is less fun code to read. I don't see any operations yet, though. It's just twiddling data. What's going on? Oh, here, check dir, check open for the root. Where is it actually doing anything? Like I'm looking for. I guess we could ask AI. Found. Oh, T, it's iterating over dirs and files. Okay, so I think it is just...
Is it just checking if the file exists?
Yeah, maybe it is. But you have this like open dir and check dir methods, but what are using those? These are actual tests. Oh, I guess, I mean, I don't know. Huh. Oh, well, because file system, so they've added this interface to the FS package where you can say sub to get basically like a sub file system. Basically, give me a file system object, but it's rooted in this subdirectory path. And because of that, when I saw dot, usually that means the root. It's kind of like just having slash. And if they did that once, then that would just be at the root. But if they're doing it in a loop for every directory, it means they are checking every directory. Okay, anyway, so it looks like they at least check that open works and readdir works, and that there's, looks like it checks to see if names are valid. Anyway, okay, that's interesting. So this is cool. It's like a generic file system tester, and I was waiting for something like this. What utilities did I make, or rather that I borrowed from a Pharaoh? Let's see. We've got a readfs. So it looks like this is a helper that takes a file system, walks it, and then gives you a map representation of the file system, where it's just every path to string. It seems like that's kind of helpful for tests if you want to make checking specific files or something in the file system a little easier. And then what check? It looks like I made my own test file system where you get a file system. And here it looks like, though, it is checking the contents. So I could give it a map where every path in that map so these are basically just some utilities that I made for writing tests. I guess I'll also copy these over as needed. Like, we'll wait till we actually write tests. Okay. Cool. Maybe we're done with this file system package for now. Which we didn't actually write a lot of code for it, and that's nice. So why don't we use it? And we'll use it to make a Fuse file system. Fuse is a kernel extension that lets you define file systems in user space, because usually file systems are a kernel thing on, Linux and stuff. So Fuse lets you have a program that can define a file system. So this is what we will use to, it doesn't work on Windows yet, but at least for Mac and Windows, this will work. But yeah, well, basically let's use this file system abstraction to make a file system. We could do an in-memory file system. What was it? So I guess one of the reasons why I was thinking of wrapping this is because mapfs is in a test package. So it's weird to be using, this is made for tests, but we're using it for non-tests. I kind of need to see code for how they use this, which if you look at tests, so this is in fs test. Okay, imported. So I guess kind of the nice thing is that because it is a it's a type derived from a map, is that it can be declared as if it were a map. So syntactically, it's kind of nice. We don't have to like create a new struct and then set some field or whatever. Well, whatever, here's a file system. So that's a file system. And then we want to run it. So Fuse, let's see, where is Fuse? That might be another thing to copy over. I use this Fuse library called Go Fuse. And then I made this at some point. Looks like it's one file. I'll just copy. Oops. We'll make a new package called Fuse Kit. Because Fuser doesn't work for me. Fuse Kit. And then we need to make sure that we are we have those. But basically all this is an adapter to implement what Fuse needs. So if you implement a Fuse file system, you have to implement a certain API. It's much more complicated than this API. But because we are creating all of these implementations implementing this API, it'd be really nice. We could just say, we create an adapter basically that says, given one of these file systems, it'll create the proper Fuse file system. So I think this is read-only, but it will probably be good enough. And then this is an example program for how this is set up. So given a file system, it's unfortunate it's also called FS, but more or less that's all we want. We'll just hard code this other stuff. So we're going back into our serve, and what the hell just happened? This is our file system. Let's see where there are options. Fuse kit. We'll just mount at Wanix for now. And then let's see if we got the right FS. Yep. So in theory, now if we run serve, I don't know if we have permissions for /Wanix, but we should get a file system that has a file and then a couple of directories with a file. Let's see, go build command Wanix. Serve. There was no error. Let's see. /Wanix. Nope, it didn't do it. That's weird. It could be a permission thing, but you would think we would have gotten an error. Huh. Let's make sure. So that's interesting. It's not even getting there. It could just...
Question. When we are building the file system, why are we using mapfs?
Sorry, what?
In the code.
Are you talking about this FS? Or...
The mapfs up
this
there.
One? Because it's... we're just testing this out. We just want to get a file system.
Oh, okay.
Mount, it's like doing the hello world. It's like do incrementally, and then because already it's not working. So if we were to do all this other stuff and try and test that, it's like, oh, this at least means that it's not even getting to this point. It could be that it's. I know that when you mount on a lot of these platforms, the directory has to already exist. So maybe if I... okay, so it's complaining because root is probably a read-only file system. I think there is no Wanix, right? No, okay. We can do temp Wanix, right? Wanix. Yeah, okay, let's try that. Still not getting to mounted though. Mounts it on the drive. Start serving requests. This is a convenience wrapper. Oh, maybe wait is maybe it's gonna block, and wait is just for extra cleanup. Yeah, I think mount already calls serve. What's going on here? Mount fuse server. Okay. We're almost coming up on time, but if we can get this working, it's kind of like the perfect way to end. Is it not up? Maybe it is in here. Nope, nothing in it.
Do we have to build it again?
Up. Okay. So there's a bunch of logging stuff in there, but it looks like mounted. So I'll take this out. So we're gonna get a bunch of stuff as we use it, but it looks like, look at that. So there's a hello file. We can cat hello, and that's hello world. And then there's a fortune and a K, fortune, K. Right, we could even, I mean, it's a file system, so it's like we could open Vim, you know, if it was a, I think I think this mapfs is read only. That's something that we'll see. Like, I think if we, like, I can't make a file in here. Yeah, permission denied. So that's one constraint of mapfs, is that it's read only. So that is a good reason why we will have to do our own like memory file system. We can base it, we can build it around mapfs, or maybe even just like borrow the implementation. But this is a pretty good stopping point, because we started the project, or we kind of reset things. We made a little CLI and serve, which right now serve means serve the file system. That file system is just this in-memory thing. We're not doing anything cool yet, but the fact that we're able to mount a fuse file system that implements the FS abstraction, the cool thing about this little adapter and this interface is the more things that you write, or adapters and stuff that use an interface, that means the more things you can do with it. So like normally, if you wanted to implement a fuse file system, you would have to implement their API, and it's much more complicated. And so it'll probably be a one-off thing. Whereas here, because we made this adapter that uses the FS API, it's almost like we don't have to write any code to get it working in Fuse. We can just drop in anything that implements FS, and we'll get a working Fuse file system. And the same for 9P and other stuff. So that's kind of, again, we talked about the benefits of interfaces. But anyway, this doesn't really explain where we're going. The next session will... do I have it in here? Now that we have the file system abstraction that we're going to use and a working fuse and CLI, we can start building the core of the new Wanix, which is based around this namespace file system implementation that works like Plan 9 namespaces. So we'll probably do that maybe Wednesday. We'll try skipping a day this week. But we can continue this on Wednesday. Does that sound good, Tara?
Yeah, I think so. Yeah, that should be fine.
Let's see, anything else? I guess.
It's nice to see how file system logic actually works.
Yeah.
So I was like thinking I'll just take time to go over in this code base and look around and understand more, get
Yeah.
into the methods, like actually go into some methods and see how they are working.
Yeah. I guess I'll push this to the repository. It'll be under the 03 branch. I'm just realizing the way I set up OBS, I have audio. So I think some of our conversation was cut out. If anybody in chat can confirm that, which means maybe the early part in the stream, we missed some stuff, but next time it'll be better. But I guess for now,
Cool. Good progress.
yeah, I'll yeah, you guys can hang up. I'm gonna kind of let this outro a bit here.
Okay, bye.
Yeah, thanks guys. See ya.
Thanks.